All right, today we're going to dive into one of my favorite tools in all of geometry, special right triangles. Now, these are not your average everyday triangles. No. Think of them more like mathematical cheat codes. They can save you a ton of time and effort, and trust me, once you know what you're looking for, you're going to start seeing them absolutely everywhere.
I mean, just look at the world around you. That building across the street, the bridges you drive over, it's all geometry in action. And you know what the real hero of so many of those designs is? The triangle. It's like the bedrock of engineering because it's just so strong and stable. But here's the cool part. Some of these triangles have, well, special properties that engineers and mathematicians use as these amazing shortcuts. They let you solve really complex problems with super simple, repeatable rules.
So here's our game plan. First, we'll talk about what makes these triangles so special. Then we'll tackle the 45-45-90 triangle, figure out its formula, and try it out. After that, we'll move on to our second VIP triangle, the 30-60-90. Sound good? Let's get started.
Okay, first up, introduction to special triangles. So what exactly makes a right triangle special? I mean, really? Well, it's not about how they look. It all boils down to these super predictable and consistent relationships between their angles and their sides. And it's that relationship that's going to make our lives so much easier. And that is the key right there. The whole point is to avoid pulling out complex trigonometry, sine, cosine, tangent, for every little calculation. With these triangles, we get these awesome fixed ratios. What does that mean for you? It means if you know the length of just one side, you can figure out the other two, boom, just like that, with some simple multiplication or division. They are, quite literally, geometric shortcuts.
So let's dive into our first one, the 45-45-90 triangle. And yeah, the name kind of gives it away, doesn't it? Its angles are always going to be 45 degrees, 45 degrees, and, you guessed it, a 90-degree right angle.
Okay, so what's really cool here is what this tells us about the sides. There's a fundamental rule in geometry that says sides opposite equal angles are also equal. Makes sense, right? And since we've got two 45-degree angles, the two legs across from them have to be the same length. And that, my friends, makes the 45-45-90 triangle an isosceles right triangle. For now, we're just going to call the length of those legs A. All right, we're now deriving the hypotenuse. So we know the two legs are equal. That's step one. But the big question is, how do they relate to the hypotenuse? That long side opposite the right angle? Well, to figure that out, we get to call on an old friend, probably the most famous theorem in all of math. You know it. A squared plus B squared equals C squared, the Pythagorean theorem. This is the key that's going to unlock the whole secret of the 45-45-90 triangle. It's that beautiful rule that tells us for any right triangle, you square one leg, add it to the square of the other leg, and you get the square of the hypotenuse.
And check out how perfectly this works. Since we already know both legs have the same length, which we're calling A, we can just plug that right into the theorem. So instead of A squared plus B squared equals C squared, we get A squared plus times A squared equals C squared. See? We just combined those A squared terms, which gives us 2A squared equals C squared. And to solve for C, all we got to do is take the square root of both sides. And that simplifies right down to C equals A times the square root of 2.
And bam! There it is, stated all nice and formal as a theorem. This is the shortcut, people. This is the whole point. If you see a 45-45-90 triangle, you can forget about running the Pythagorean theorem from scratch every single time. Just take the length of one of the legs, multiply it by the square root of 2, and that's your hypotenuse. It's really that simple. Okay, time for some practice. Theory is great and all, but let's actually put this theorem to work. It's time to solve for some missing sides. So, take a look at these two triangles here. On the left, in triangle A, we know the length of a leg. And on the right, in triangle B, we know the length of the hypotenuse. So, how would you use our new rule to figure out those missing sides? All right, let's start with triangle A. This one's pretty straightforward, right? Since we know it's an isosceles triangle, if one leg is 5, well, the other leg has to be 5 too. Easy. And to get the hypotenuse, we just use our rule, leg times the square root of 2. So it's 5 times the square root of 2, and we're done.
But now, what about that second triangle? This one's a little trickier, right? Because here we have to work backwards. We have the hypotenuse, and we need to find the legs. So the key here is setting up the equation correctly. We know our formula is hypotenuse equals A times the square root of 2, and we're told the hypotenuse is 6, so we just write it out, 6 equals A times the square root of 2. To get A by itself, we just divide both sides by the square root of 2. That gives us a equals 6 over the square root of 2. Now, in math, we have this little rule. We don't really like leaving a square root in the denominator of a fraction, so we have to rationalize it. And that sounds fancy, but all it means is we multiply the top and the bottom by that square root of 2. When we do that, we get 6 times the square root of 2 on top and just a plain old 2 on the bottom. That simplifies down perfectly to 3 times the square root of 2. So that's our answer. Each leg is 3 root 2.
Awesome. You've totally got the 45, 45, 90 down. So let's introduce our second special guest for today, the 30, 60, 90 triangle.
Okay, so when you look at these two side by side, you can see a major difference right off the bat. Our first triangle, the 45, 45, 90, was isosceles, right? 2 equal sides. But this new one, the 30, 60, 90, has 3 different angles. And what does that mean? It means it's also going to have 3 different side lengths. It's what we call a scalene triangle. So here's the deal, the big theorem for the 30, 60, 90. We're not going to walk through the whole proof this time, but the rule itself is just as powerful. It gives us a whole new set of relationships, and here's the most important part. Everything is based on the length of the shortest leg. Once you know that, the hypotenuse is just double that short leg. And the longer leg? That's the short leg multiplied by the square root of 3.
This diagram right here, this is the one you want to burn into your memory. See how everything revolves around A? That's the shortest side. If you can figure out what A is, you can find the other 2 sides in a snap. It's the anchor for all your calculations. Find A, and you've solved the puzzle.
And if you're worried about mixing things up, here is the absolute best way to keep it all straight. Just remember this, the sides and the angles match up. Smallest side is across from the smallest angle. Medium side is across from the medium angle. And the longest side is across from the biggest angle. So the shortest side, A, is always opposite that tiny 30-degree angle. The medium side, A root 3, is opposite the 60-degree angle. And the longest side, the hypotenuse, 2A, is always opposite the big 90-degree angle. That logic will never, ever fail you.
So let's put it all together in one place. Think of this table as your ultimate cheat sheet for special right triangles. For our 45, 45, 90, the side ratios are simple. A, and A root 2. And for the 30, 60, 90, just remember that order we talked about. A root 3, and 2A, which match up with the sides opposite the 30, 60, and 90-degree angles.
And just like that, you've unlocked 2 of the most foundational concepts in all of geometry. Seriously, these triangles are like building blocks that pop up everywhere, in physics, in engineering, in design. So the next time you see a ladder leaning against a wall or a support beam on a building, I want you to take a closer look. You might just spot one of these special triangles hiding in plain sight. So now you got the shortcuts. The only question left is, what problems are you going to solve with them?